Welcome friends. I welcome again you in the next session of our normal distribution and its application along with its property. In the previous session you have enjoyed the you have enjoyed with respected Professor Ashok Shah. There have discussed already some property and its application with the long history of the normal distribution, which is one of the most applicant distribution. Let us again see some more properties with having some flashback of the previous session, and we will again see some application of normal distribution again along with it. So let us start our journey. Here again, history of the normal distribution. The most important continuous probability distribution used in entire field of statistics is the normal distribution, and the founder was respected Carl Friedrich Gauss during 1777 to 1855. Again, the normal distribution is often referred to as the Gaussian distribution in honor of Carl Friedrich Gauss. Here this fellow has studied some distribution of errors. So that's why this normal distribution is again also called as a distribution of error, that we will see by one activity afterwards. Here again you know the normal density. The normal is a theoretical distribution specified by its two parameters, respectively mean mu and sigma square. Here variable x can take value minus infinitive to plus infinitive, and PDF is given as you can see 1 upon root 2 pi sigma square multiplied by e raised to minus x minus mu square divided by 2 sigma square. Now the normal distribution with mean mu and variance sigma square may be also denoted by the symbol n for normal, mean mu, and sigma square is variance. Here the PDF fx greater than 0 for all value of x, and the integration of this PDF fx in the range minus infinitive to plus infinitive is equal to 1, and the parameters again mu and sigma of the normal distribution are the mean and standard deviation of the distribution respectively. Here let us discuss some properties. Symmetrical property means the normal curve is a symmetric. Again its mean it is more clarified by this pictorial view. Here you can see that mean, median and mode are equal and located at the same point. Now normal curve is again symmetrical with two halves identical. Here you can see the tail parts also, it is not touching the x-axis but it is quite asymptote. And here theoretically the curve ends to minus infinitive to plus infinitive. So that was that. Again next property is bell shaped, already discussed. Here the curve of the normal distribution is having a bell shaped curve. Similarly tails are asymptotic. It means that they never touch the x-axis. You can see this figure, they never touch the x-axis. Okay, next property was mean and median and mode are equal. Let us have an example. Here this example is for final grades in social statistics of 1200 students during 1983 to 1993. Here in the first column midpoint scores are given, which are 40 up to 100, and for our convenience I have included the frequency bar chart here. and after the subsequent two columns you can see the frequency and cumulative frequency also. Now problem is how to check the normality. It means that how to decide whether the data is following normal distribution or not. Here, for this checking, to overcome this question, we will have to initially examine two things. First is look at the shape illustrated by the bar chart or histogram. So here you can see the bar chart. The bar chart is again having the shape like bell shape. It is again one property of normal distribution. So it is enough to say that your data is following normal distribution. Again, the second point is to calculate the mean, median and mode. If mean, median and mode are equivalent, means are somewhat same, then you can say that the data is following again a normal distribution. Here in our case, mean is 70.07, median is 70 and mode is also 70. So they are approximately same. So it is quite enough to conclude that our data is following the normal distribution. Again, here since all three are equal and it is reflected in the bar graph, we can assume that again the data is normally distributed. Okay, that we have already discussed. Now next is also since the median is approximately equal to the mean, so it is quite enough to conclude that our distribution is symmetrical, means the two halves are identical, or if you will fold your curve from mean, it will give you a mirror image of each other. Again, from the pictorial view, it is more clear that mean, median and mode are equal, curve has bell shape and asymptotic to the x-axis, never touches the x-axis. Okay, this property is unimodal, means our distribution have only one mode, that you can see in the figure A. So in case of normal distribution, here the curve has only one peak point, means only one mode, that you know. And in either of the cases, means in the non-normal condition, you may have bimodal as well as trimodal curve, means your curve may be having two peak points in the curve and also three peak points in the curve in case of non-normal data. So it is now clear that in the case of normal distribution there will be only one mode, means this distribution is unimodal, means have only one mode. Okay, next is total area under the normal probability curve is 1. Again, the ordinate at the mean of the distribution divides the total area under the normal curve into two equal parts. Let us see here, from the ordinate of mean, total area is divided into two equal parts, two identical parts, or you can say it generates mirror image from the mean. So if the total area under the normal probability curve is 1, each separated area from mean will have probability 0.5 each. Now next, let us see some descriptive measures for normal distribution. Here mean is equal to x bar or mu and variance is denoted by mu2 or sigma square. Friends, you know the formula for mean and variance respectively, right? Now third central moment, mu3 is always 0 for normal distribution, as well as fourth central moment, mu4 is equivalent to 3 sigma raised to 4 or is equivalent to 3 mu2 square, because mu2 is equal to sigma square. You can see this is the variance, notation for variance. Now again let us see the skewness. skewness beta 1 is equal to mu 3 square divided by mu 2 cube, that you know the formula, which is 0 in the case of normal distribution. So you will be having the normal curve as described in this figure extremely left, right? So in case of normal curve, you will be having the first figure from left. Now if your skewness beta 1 will be greater than 0, in that case you might be having the positive skewed data. Positive skewed data means your extreme right tail will be quite longer than that of left tail of your curve. So in that case, most of the data will be situated or located, or you can say concentrated upon the left part of your curve. Similarly, if your beta 1 is having this value less than 0, means you will be having the negative skewed data. So in case of negative skewed data, your left tail of the curve will be quite longer than that of right hand side of tail. So in the case of negative skewed data, total area will be more concentrated upon the right hand side of the curve. So in case of normal curve, most of the data will be centralized around the mean, you can say. Oh, it is very easy to see from these figures. Now next, kurtosis. Next is kurtosis. So kurtosis is beta 2 is equal to mu 4 upon mu 2 square, that you know in case of normal distribution it becomes is equal to 3. So you can see the green part, mesokurtic curve. So you can have this type of curve whenever your beta 2 will be is equal to 3. If your beta 2 will be less than 3, then you will be having the platykurtic curve. You can see the figure, friends. And in case of beta 2 greater than 3, you will be having leptokurtic curve. So here you can see the general forms of kurtosis. So wherever you will be having platykurtic curve, your data will be quite skewed with respect to the leptokurtic or mesokurtic curve. Whenever you will be having the leptokurtic curve, the thickness of the curve will be quite taller, you can say that, and in that case you may have less skewed data, means the spreadness of the curve will be less than that of platykurtic curve. Okay, now let us see the quartiles property. The quartiles Q1 and Q3 are equidistant from the median. It means that the distance Q2 minus Q1 is equal to distance Q3 minus Q2. Or in either case, means if your data is following not normal distribution, you may be having positive skewed data as well as negative skewed data. It is given in the figure that your quartile Q2 will be quite near about Q1 in the case of positive skewed data. Wherever at the other hand, if you will be having negative skewed data, your Q2 will be quite near about Q3. It means that in case of non-normal data, the distance of Q1 and Q3 never be same about Q2. Okay, now it is asymptotic to the baseline x-axis on its either sides that we have already discussed, and as the distance of the curve from the mean increases, the curve comes closer and closer to the x-axis but never touches it. Keep it in mind that, but never touches the x-axis. Let us see this figure here. See these tail parts. So here the tail parts are quite far away from the median location. So this tail parts curve is quite near about the x-axis. You can see here nearby the mean, the curve part is quite far away from this x-axis. Clear that? Okay, next here remember this PDF because we are going to use it. Okay, so in this PDF the power of this exponent have negative sign, right? So if we want to maximize this function of x, you will have to maximize this total exponent part, and the power of this exponent will be maximized at 0 because here there is minus sign, right? So e raised to 0 will be 1, but when it is going to be happen? So if you are taking x is equal to mu, if you are taking x is equal to mu, at that time you will be having e raised to minus mu whole square divided by 2 sigma square. It is going to be 0, means the power of this exponent is going to be 0. Now e raised to 0 becomes 1, and you are having your PDF at maximum is nothing but 1 upon root 2 pi sigma, or you can say that 1 upon sigma into root 2 pi. If you are taking out this sigma square from the square root, it becomes sigma. It is quite obvious. I repeat, okay, this power is negative and we want to maximize this function of fx, means here whenever you will be taking x is equal to mu, then the power of this exponent becomes 0 and e raised to 0 is equal to 1. So again we are having this function, maximize of this function where 1 upon root 2 pi sigma square in square root, or you can say 1 upon sigma root 2 pi if you are taking outside this sigma square. Okay, now thus the maximum value of fx is inversely proportional to the standard deviation. Let us see here, because the standard deviation sigma is in the denominator, this fx is inversely proportional to that standard deviation sigma. Okay, now it means for small values of sigma, PDF means fx increases, and it means the curve has a sharp peak, and for larger values of the sigma, fx decreases. It means the curve is going to be more flatten and flatten. Let us see this using this figure. Here the standard deviation is small, so the curve has more peakness, and in either case this sigma is quite large, means the spreadness of the curve is going to be high. It means your curve is becoming more and more flattened. Okay, here additive or reproductive property. Here the sum of independent normal variates is also a normal variate. It means that if you have n independent normal variates, say x1, x2 up to x small n, and if you are adding this all n independent variates, so this is also following the normal distribution. Here the mean of that sum of all independent normal variates will becomes the sum of corresponding variates mean, means mu1, mu2 up to mu n, all are the individual means for independent normal variates. So just add up, means just have a summation of that all means. Similarly the variance is also a variance added by all that individual variances, means sigma 1 square, sigma 2 square up to sigma n square. Okay, now let us see area property, which has been already discussed in the previous session by respected Professor Soksa sir. Let us see. About 68.26% of the area under the graph is within one standard deviation of the mean. It means the range is mu plus or minus sigma. Let us see. Here from this figure, within one standard deviation of the sigma from mean mu, we are getting almost 68% observations in this area under the curve. Next is about 95.44% of the area under the graph is within 2 standard deviation of the mean. It means the range mu plus or minus 2 sigma. Let us see. Here within the range mu plus or minus 2 sigma from mean, almost 95% of the observation will be following within this range. Similarly, about 99.72% of the data will be fall within mu plus or minus 3 sigma range. You can see here about almost all data will be covered within 3 sigma ranges. Hence, for practical purposes, the range mu plus or minus 3 sigma, which covers the entire area, almost all area, which is taken as 1, because rest of the all observations may be negligible. So this mu plus or minus 3 sigma property, this area property, I think that